Today we are diving deep into data science, machine learning, and generative AI. Now, I know for you watching this or listening to this, it might sound a bit intimidating, like science fiction. But here's the thing, right? Every single decision human has ever made, think about ancient civilizations trying to predict harvest or modern businesses trying to forecast sales, it's always been data-driven in some way. You have always used information, we have just gotten faster and more accurate. If you look back, those early communities, they were instinctively using data, things like geography, rainfall, patterns, temperature, etc., to figure out when to crop plants or, for example, to stock firewood. Business today fundamentally are doing the same, and we are using incredibly sophisticated methods and frankly huge amount of compute power. It's more like an evolution than a sudden revolution. So my mission today really is to cut through the complexity. I want to equip you with foundational knowledge, stuff you need to really understand these powerful tools and see how they can actually be used, see the practical business applications, and this is crucial, understand the limits as well. So to start, it's probably helpful to think about two main ways data science tends to approach problems. We generally call them inferential paradigm and computational paradigm. They may sound technical, but the core ideas are actually pretty intuitive when you break them down. So two different ways of using data, keep that in mind. So the inferential paradigm is usually all about drawing conclusion or make educated guesses about a bigger picture based on just a small sample of, okay, think about your own brain. How does it work? It's constantly learning general rules just from specific things that it observes, or a doctor diagnosing an illness. They don't need to see every sick person with that illness. They take a look at the symptoms that you have. They have a huge knowledge of medical cases, and then they infer what's going on within you. So it's learning from specifics to understand the general. Now you may be wondering, how would I as a business use this, right? How can I take a small sample and then define a general rule? A classic example in the business in when you introduce a new policy for your employees. You probably can't survey everybody to see what's the impact of that policy on employee morale. So you're going to take a small sample which is representative of your company. You're going to survey that, and you will infer from the results how the entire staff probably feels based on that sample's responses. Or, for example, testing a new product, you might run a small control poll program in one city and to see if it will be successful, and then infer if you can watch it succeed nationwide. We are going to use the word infer a lot. For those of you who are not Anglophones, it means deduce or guess, conclude from evidence, or derive by reasoning. Remember always the educated guess that we said. Infer is the educated guess. So that was inferential. Then there is the computational approach. Computational data science, that leans heavily on technology and algorithms. It's about processing massive amount of data that we call big data as well, to make predictions or generate insight, often at scale and in real time. Think about your brain again, but this time imagine navigating a really complex, busy street, which can be sensory overload. Your brain is rapidly processing this huge flood of sensory information, visual cues, sounds, and also related with past experiences to make decisions in a few seconds. Computational is like that for data. It tries to process everything it can very quickly. Now, you may be thinking, how does a company use this kind of large-scale processing? Weather forecasting is a great one. It crunches historical patterns, real-time satellite data, temperature readings from sensors all over the globe, tons of data to predict what the weather might do next. Or think about a logistic company like UPS or FedEx optimizing delivery routes to save fuel and time, processing massive amount of map data, real-time traffic, delivery schedules, running complex algorithms to find the absolute most efficient paths, and even constantly update them maybe. So you really need both approaches, inferential and computational. And what's really fascinating, I think, is that underneath these buzzwords like AI, machine learning, all of that, you find these fundamental mathematical and statistical theories. And precisely, they aren't just abstract academic concepts, they are the absolute bedrock of these technologies. And honestly, understanding just a few key ones can give you a real advantage in thinking about your business data. Let's talk basics. Probability is foundational. Probability is just the measure of how likely something is to happen. Your brain, it kind of does this all the time without you thinking about it. Like you take a look at the sky and say, is it going to rain today? Or for business, what's the likelihood that this customer will click on this specific ad based on what they have been browsing on the website before? So if I look at thousands of credit card transactions and maybe 10 of them turn out to be fraudulent, then the basic probability of any random transaction being fraudulent is just 10 out of 1,000 or 1%. That is simple probability calculation. But then it gets more interesting as you add more information. What if we know a transaction is fraudulent? Does that change the odds of it being a specific type of fraud, like a phishing scam or a credit card that is stolen? So knowing one thing changes the probability of another, and that's called conditional probability. It's the likelihood of event B happening given that event A has already happened. So back to the fraud example. If you know a transaction is fraudulent, that's event A, what's the probability is specifically, for example, phishing scam, event B. Maybe you look at your past data and find that 35 out of 50 confirmed fraudulent transactions were phishing related. Okay, 35 out of 50, that's 70%. So given that a transaction is fraudulent, there is a 70% conditional probability it's a phishing scam. You have refined your understanding based on that new piece of information, the fact that it was fraudulent. And this idea of refining probability with new evidences, that's brings us to Bayes' rule. Bayes' rule it's a really powerful mathematical formula for systematically updating your initial probability estimation as you get new evidences. It's how AI systems often learn and refine their guesses. Let's use your immune system as an analogy. Your immune system might initially have a general sense of a threat like a virus, but as it gets more information, specific symptoms, maybe antibodies being produced, it updates its assessment, its probability of which specific virus it's fighting. Bayes' rule is the math behind that kind of updating processes. Now, let's take another fascinating kind of example involving a medical test. Imagine there is a disease, but it's quite rare. Only 1% of the population has it. And that there is a test for it, and it is pretty much accurate. It catches 80% of true cases. But it also has a 10% false positive rate, meaning 10% of healthy people will test positive anyway. So it's making mistakes. Now, here's the question. If you take the test and get a positive result, what's the actual probability you have the disease? Your intuition says the test is 80% accurate, so maybe around 80% I have that disease. But when you apply Bayes' rule, factoring in that low 1% Bayes rate and the 10% false positive rate, the actual probability you have that disease, even if you test positive, is only 7.5%. That's completely counterintuitive. And it is critical reminder, especially for businesses, that you have to question these headline probabilities, understanding the context, the base rate, potential for errors, especially in things like diagnostic or fraud alerts. It's not just about the number, it's about understanding how you got to that number. And that leads us nicely into descriptive stat, things like mean, median, mode, standard deviation, right? These are basics. When you think about your brain, it's not averaging every single minute. It's probably using mode, the most common type of day, or maybe a median, for example. Or your body knowing its average temperature, it's the mean, but it also knows how much that temperature naturally fluctuates. That variation is captured by the standard deviation. So let's quickly break these down. Mean is just the average. Add everything up, divide by the count, like average employee salary. Simple enough, but here is the thing about averaging. Relying only on the mean can be incredibly misleading. Imagine your company's salaries. If you have a few executives with exceptionally high salaries, even if they are 2 or 3, these salaries can pull the overall average way up. It is called the outlier effect. Outlier is a point in a sample widely separated from the main cluster of points in the sample. Imagine 90% of your employees are paid 65K, then you have 5% who are paid 600K. That 5% is going to bring your average to 92K. So the average salary might sound great, but it doesn't reflect what most people actually earn in your company. It gives a skewed picture. So for more realistic view, especially when you have outliers or skewed data, you look at median, which is the middle value if you line everything up. If you list all of the salaries that you have, the middle salary is 65K. So the few executives who have high salaries don't distort the median nearly as much. It gives a much more typical picture for the rank and file employee. Now, mode is simply the value that appears most frequently. It's usually for non-numerical data, like finding the most popular product color. And standard deviation tells you how spread out the data is. In other words, how much variation there is around the mean. A low standard deviation means data points are clusters close to the average. A high standard deviation means they are spread out over a wide range. This really underlines that the warning about deceptive statistic. Some could choose to present that mean salary instead of the median precisely because it looks better, even if it's misleading. You always need to ask which average are they using and why. Does it make sense for this data? So understanding the distribution is key. Another foundational concept is matrices and linear algebra. This helps computers see and organize information. Think about how your eyes see an image. It's really processing millions of tiny points of light, each with a specific color and intensity. So a computer sees an image in a very similar way, representing it as a grid or multiple grids of numbers, which is called matrix. Each number might represent the intensity of red, green, or blue light at a specific pixel location. So images are just big spreadsheets of numbers to a computer. In essence, a vast numerical array. And it's not just images, your regular business data like a spreadsheet or a database with rows for customer and columns for the attributes, that's also fundamentally a matrix. Now, you may be asking, why is thinking in matrices useful? Because linear algebra gives us powerful tools to manipulate these matrices. This is an absolute fundamental for things like image processing, facial recognition, quality control on an assembly line. And it's also how recommendation systems work. They often represent users and products as matrices to figure out which products you might like based on users similar to you. One more foundational concept before we get to the really fleshy stuff is dimensionality reduction. It sounds like simplifying things, and that's exactly. Imagine you're trying to describe a person to someone who has never met them. You wouldn't list the exact position of every single atom in their body, right? That would be overwhelming and useless. Instead, you'd focus on the most important distinguishing features like hair color, height, maybe key personality traits. Your brain instinctively filters out the unnecessary details. Dimensionality reduction does the same thing for data. It finds the important features and ignores the noise. It identifies the most informative aspects, the dimensions and variables that capture the most variations or information, and discards the ones that don't add much value or are redundant. Dimensionality reduction is already at work in nature. Insects and animals do not filter light, for example, the same way as human eyes do. Their brains are specifically evolved to pick out the most crucial information for survival. It's about what's necessary for survival and function, not just what's possible. Bees and other animals have evolved to be incredibly efficient with their limited neural resources. They reduce the dimensions of sensory inputs like seeing to ultraviolet or specific colors and not everything which is possible. It's not solely because they can't process everything, but because processing only the critical information is more adaptive. They can see, for example, a predator way quicker, and they can distinguish patterns way easier. Our data science algorithms, in a way, aim for that same kind of intelligent efficiency. And why would a business owner care about reducing dimensions? First, it cuts through the noise. If you're tracking about 500 different attributes about a customer, it's overwhelming. The dimensionality reduction might find that only, say, 10 to 15 of those attributes really matter for predicting if they'll buy something. So it makes the data more manageable and interpretable. It saves the storage space, and it makes your algorithms run much faster because they have less data to process. And sometimes it can even improve the accuracy of your models by removing irrelevant noise that might confuse them. Think about visualizing complex sensor data. Reducing it to 2 or 3 key dimensions makes it possible to actually see patterns. Simplified to clarify. So we have laid the groundwork: probability, stats, matrices, simplifying data. We will build on that in the next episode. If you're feeling inspired and ready to get a bit more hands-on, maybe explore these concepts further in a practical way, you can actually enroll in our upcoming hands-on session. I'll put the link below. It's a great way to take the next step, and definitely join us next week for going further and using the concepts that we learned today and see how they are used in machine learning, deep learning, and generative AI. Our deep dive will then focus on data, which is absolutely foundational for all of these technologies, we will be talking about how to define, gather, clean, and prepare the right data for your specific business solutions. I hope it was useful for you. Enroll in hands-on sessions if you would like you, and see you next week.